So, welcome back to this course on advanced manufacturing and process modeling. So, we were discussing about the die filling different principles of how to get a sound cast part with the desired level of mechanical properties and structural integrity. So, we have already discussed about the basic principles about in the last class. So, we will continue with this class. We will start with the porosity modeling aspects. So, so porosity basically it generates within the solidifying dendrite mush because of the that saturation level in the of hydrogen within the liquid melt that drops the moment the temperature cools down. So, within the solidifying melt which is basically generates it is basically generates in the interdendritic spacings, and also the shape of these pores which are you can see over here. So, the shape of these pores also is generally determined by the shape of the evolving dendritic mush, and you can see that finally they are getting trapped into the primary dendritic arm spacing between two adjacent dendrites. This is the trapped region, is basically the region where the pores are forming. So, here this schematic is basically depicting the porosity formation mechanism in case of a aluminum copper alloy with columnar dendritic interface. So, what actually happens, so basically this is the porosity in the mushy zone is modeled here as the formation of gas bubbles. So, the driving force is supersaturation pressure of the gas. So, if you recall that one of the initial classes I have discussed about the sources of gas formation within the solidifying melt is because of the for several reasons. In case of sand casting, it may be because of the moisture content that is present within the mold. It is maybe because of the from the core, the additives which are used for the core making, because of their evaporation and burning, gases can be generated. And the one of the most primary source, if we are talking about light metals, for example aluminum alloys, then it is hydrogen. So, so these are the so the saturation pressure of the these evolving gases is the driving force for pore formation. So, here which is termed here as Pg, and Pg is basically equivalent to the Pi minus Pie. So, what is Pi? Here Pi is the real pressure of the gas in the mushy zone, and then Pie is the equilibrium pressure of the dissolved gas in the mushy zone is equal to K, that is the equilibrium constant, into Clg, again the real gas concentration in the liquid minus the equilibrium gas concentration in the liquid melt. So, this is how we can determine the value of the supersaturation pressure which is the driving force, that is Pg. So, here there are several other forces which are basically assisting, and there are some forces which are basically trying to compress or trying to negate the pore formation within the solidifying mush. What are those? That we will learn in the subsequent slides. You can also see over here. So, that is basically the force due to the shrinkage of the solidifying mush. There is force due to the atmospheric pressure, and also due to the metallostatic head that is present within the solidifying liquid melt, force due to surface tension, and also force due to the thermal contraction of the dendritic mush which is solidifying. So, so here the study by Jacobi concluded that primary dendrite arms align in an interlocking manner, that we have seen in that first schematic. So, you can see, so this is basically this is called the interlocking solidification mechanism of this dendritic mush, and then bubbles are accommodated in the interdendritic space. So, as I told you earlier that the radius of curvature of these evolving pores or bubbles is basically governed by the shape of the secondary and primary dendrite arms. So, here the principal radius of curvature for the bubbles. So, here pores are referred as bubbles fitting in the interdendritic space is given by small r is equal to Fl gamma delta 1 by 4. So, yeah, I mean, so lambda 1 here is the primary dendrite arm spacing, FL is the volume fraction of liquid. So, this is how from this formula we can basically determine the radius of curvature of this evolving pores or bubbles. And then, so the total driving force for gas bubble formation is can be defined as Pb, which is equal to Pg, that is the supersaturation gas pressure within the liquid melt, minus. So, this is basically, so as I told you earlier that there are some forces which are basically promoting pore formation and there are some others which are serving as to nullify or to compress the pore size. So, Pg is a supersaturation gas pressure, it is of course the driving force for pore formation, minus. So, these are basically the nullifying force or who are trying to negate the pore formation, that is the atmospheric pressure P at M, and then that surface tension force and then the metallostatic head. So, plus these two. So, these are again helping for the pore to pore formation, that is force due to shrinkage. So, shrinkage pressure and then the P epsilon. So, this is because of the thermal contraction of the solidifying dendrite mush, this P epsilon is getting generated. So, they are individually defined over here. So, like P ATM, PST is equal to again the metallostatic head, metallostatic pressure. So, that means rho L G H, H is the height of the liquid melt above the reference point. P sigma is the 2 sigma by r. So, surface tension pressure, where sigma is the surface tension and r is the bubble radius, and pre shrinkage is the pressure drop due to solidification shrinkage, can be calculated by Darcy's law, and P epsilon is the pressure drop from thermal contraction of the dendrite network. So, once the gas bubble is stable, so then we can assume that the Pb, that means the pressure which is total driving force for gas bubble formation, Bb is equal to 0. Then from this equation, rearranging the terms, we can get, if you take these negative terms to the opposite side, then it becomes Pg is equal to P ATM plus Pst plus P sigma minus P shrinkage minus P epsilon, wherein P shrinkage can be defined as integration 1 to Fl 180 mu 1 minus Fl square by lambda 2. Lambda 2 is again the secondary dendrite arm spacing, as we already told that the lambda 1 is the primary dendrite arm spacing, square into Fl cube into Vf Fl dFl. So, this is how we can define the shrinkage pressure, and then we can further simplify it, the expression like this. So, where you can see that we have already talked about the G, that is in case of defining the metallostatic pressure. So, here G is the acceleration due to gravity, rho L is density of the melt. So, it should be the L should be the subscript. So, please correct it. H is the depth of the melt above the reference point, sigma is the surface tension of the melt, and r is the radius of the evolving pore or gas bubble. Whereas, nu is basically the average velocity of interdendritic fluid flow. So, this velocity of fluid, this flow is basically triggered by the shrinkage flow. This is also called as shrinkage flow, and it is acting perpendicular to the isothermal lines. So, the assumption, so that just for this defining this velocity, these assumptions are important. So, as I told, the flow is induced solely by shrinkage, and the second assumption is velocity can be approximated as beta into r, where r is the solidification rate and beta is the solidification shrinkage factor. So, here material properties in this definition of these pressure heads, where mu is the viscosity of the solidifying melt, delta lambda 2 is the secondary dendrite arm spacing, and Fl is the volume fraction of liquid. Okay. So, so it should be noted here that the estimation of pressure in gas bubble is partially simplified, where the pressure drop related to tensile deformation is set as the same order of shrinkage depression arbitrarily, that is Pe or P epsilon, like we have in the previous slide we have defined it as P epsilon. So, it is same. So, please correct it. So, it should be P epsilon. P epsilon is equal to omega P shrinkage. So, where omega is a constant ranging from 0 to 1. So, before gas bubble formation, a lever rule must be used for the redistribution of gas element during solidification, which can be expressed as this 1 minus omega L, small omega L into k g C L function of g, I mean that is the gas concentration, and plus I mean omega L C L g is equal to C 0 g. So, where C L g, C S g and C 0 g are the concentration of gas element in the liquid. So, here I mean solid and the average initial concentration of hydrogen in the liquid phase respectively, where Kg is basically the I mean your Kg is basically the redistribution ratio of gas element between solid and liquid phase, and I mean omega L is the mass fraction of liquid. So, with this we can move ahead. So, we can also define the critical liquid fraction as omega L C, which is equal to 1 by 1 minus Kg into C 0 g by C L C, critical liquid concentration G minus Kg. So, when bubbles present in mushy zone, hydrogen concentration in liquid and solid phase follow the solubility respectively. So, here we can define CLG is equal to 10 to the power AL by T plus BL into root over Pg, that is the I mean supersaturation gas pressure, and then CSG is equal to 10 to the power AS by T plus Bs, where AL, BL, BAS and BS these are all constants corresponding to the liquid and solid phases into root over Pg. So, a mass balance equation in the mushy zone with consideration of gas bubble formation can be written as this, where x1 minus x2, x1 is the basically the gas ejected from the liquid, minus x2 is the I mean mass dissolved in solid, that means which becomes which equals to x3, that means it is the mass consumed by gas bubble for pore formation. So, assuming that gas bubbles are generating from biatomic gas, so x3 I mean x1, x2, x3 can be defined as x1 is equal to minus CLG rho L DFL, x2 is equal to CSG, because this is the amount which is getting dissolved within the solid phase, I mean evolving dendritic mush, is equal to CSG rho S DFS, and x3 is equal to 2 dN is equal to 2 Pg by RGT DFG. So, where rho L DFL is equal to minus rho S DFS. So, rho L is nothing but the liquid density, rho S is the solid density, and this is the change in liquid fraction, this is the change in solid fraction, and CSG is equal to Kg Cl function of G, I mean I mean gas concentration in liquid, and CSG is equal to Kg CLG. So, Fs and Fg are the volume fractions of solid and gas phases in the mushy zone, and Rg is the universal gas constant. So, this is the Rg, again it should be the subscript, please correct it. And so, here DFG is equal to 1 by R2 Rgt by Pg rho L CLG into 1 minus Kg DFL. It can be further written as 1 by 2 Rgt by Pg rho L. Now, we are putting the value of Cl like we have shown over here, you can see we have discussed over here. So, that value we are putting over here for Cl into 1 minus Kg DFL, and then if we integrate it, then we can get the gas fraction, volume fraction of gas in the mushy zone, that is Fg. So, again it should be the subscript. So, please correct it. So, Fg is equal to half Rgt by Pg integration Fk to Fl rho L 10 Al by T plus Bl Pg to the power half 1 minus Kg DFL. So, in order to estimate the volume fraction of porosity in mushy zone, the relationship between temperature and liquid fraction that we need. So, how we can get it? So, we can get it from this below expression. So, this is also can be obtained by the shell solidification model. So, for example, in case of aluminum 4.5 copper alloy, the previous study indicated that the reaction is close to shell type solidification path even at low cooling rates. So, we can express liquid fraction, or we can determine liquid fraction omega L is equal to T minus Tm. T is the given temperature at which the liquid melt at present, and Tm is the equilibrium melting temperature of the melt, and divided by MC0. C is the concentration, that is initial solute concentration, K is the solute redistribution ratio, that K is the I mean solute redistribution ratio, Tm is the melting temperature of the major element in the alloy, and m is the liquidus isothermal slope. So, this is the m. So, here so this is the small m is the liquidus isothermal slope. So, meanwhile, a conversion between volume fraction and mass fraction can be deduced as the below expression, which is omega L is equal to rho L F L by rho L F L plus rho S F S. So, here L and S will be subscript. So, it should be written like this, rho L F L divided by rho L F L plus rho S F S. Okay. So, this is how we can determine the liquid fraction, I mean conversion between the volume fraction and mass fraction. Okay. And then, so the hydrogen mass here I mean converted to volume of H2. So, here we can further modify the expression we have written over here for DFG. So, you can see, so this is basically the initial expression for DFG. So, we will see how we can modify it. So, from here. So, here the volume fraction of porosity is adjusted based on the conditions. What are the conditions? That is standard atmospheric pressure, P theta is equal to 101,325 Pascal, and the standard temperature, that is 273 Kelvin, that means I mean 0 degree centigrade. So, so the volume fraction of porosity is adjusted based on these conditions. So, the modified expression will be this one. So, what was our expression? So, our expression was this, dFg is equal to half Rgt. So, what we are basically doing? As we know that Pv is equal to nRt, assuming n is equal to 1, we get Pv is equal to Rt. So, from here we can evaluate R is equal to Pv by T. Okay. And here, so we can, so here P is the standard atmospheric pressure P theta, T is the standard temperature T theta, and V here we can define as I mean Cc by 100, that is what I mean we can consider. So, in that case 100 goes this side. So, then the expression becomes like this, 100 dFg is equal to T P theta by T theta Pg, rho L C L S G 1 minus kg dFL. So, this is how we can get the modified expression, and from here we can calculate the dFg and thereby the Fg, that means the volume I mean fraction of mass fraction of I mean gas porosity within the solidifying mush. So, here these variables are explained over here. T is the temperature of the solidifying melt at any given time, P theta, T theta are the standard atmospheric pressure and temperature, Pg is the gas pressure, rho L is the liquid density, CLSG is the solubility concentration of hydrogen in the liquid, Kg is the partition coefficient of gas, and dFL is the fraction of liquid undergoing the transformation, I mean liquid to solid transformation. So, here by considering that the typical solubility and concentration of hydrogen in aluminum melt is Cc by 100 gram, that is the mass of the dissolved hydrogen at present condition has been converted to volume of H2 and at P theta. So, this is what as I mentioned in the previous slide is equal to 101,325 Pascal, T theta is equal to 273 K. So, the expression for volume fraction of porosity is obtained like this as we have discussed earlier, and then I mean from here we can just integrate this above expression and we can arrive at the mass fraction of I mean the gases, that means the porosity within the solidifying mush like this. So, if we integrate we can arrive at this expression. So, which can be solved numerically so that we can arrive at the value of the I mean the gas fraction. So, with this we have discussed how we can develop the porosity model and we can basically quantify the fraction of porosity present within the I mean solidifying melt. So, because in case of dye filling the pore evolution is of also important criteria, because our objective is to optimize the dye design in such a way that so that there is no gas absorption, there is no I mean there is minimizing the turbulence, so that again turbulence is connected with the pore formation because of the gas absorption is linked with it. So, I mean our end goal is to get a sound cast part. So, that is why we need to take care of these aspects, and out of which these defects I mean casting defects which is largely I mean originated from the gas absorption, because and also due to shrinkage. So, that can be nullified. Shrinkage we have discussed earlier also, how to we can design riser, and so that we can I mean optimize the shrinkage porosity, and then how we can I mean quantify and mitigate the gas porosity, that also we have discussed. And we will also now discuss with the help of a case study that is performed in case of die filling of gravity casting. So, you can see, so basically how we do that. So, we need to of course solve the conservation equations to I mean to simulate, to quantify the fluid flow behavior, I mean flow behavior of the I mean liquid melt within the die casting, since we are talking about gravity casting, and this is basically applied to a low superheat casting. So, we are I mean considering the flow in the superheated melt state, although the superheat is low. So, that is why during filling there is no mass exchange, that means there is no phase transformation is happening, that is what is assumed over here. So, that is why the equation of mass balance, because it gets reduced to continuity equation where mass transfer is 0, and then the momentum equation is expressed for different I mean I mean x momentum, so the different direction. So, if there is x, there is y, and there is z. So, then it can be written for x like this, for y like this, and for z it is like this. And if you can if you want to write it in vectorial notation, so you can do that as well. So, in that case you have to write like this, del v del t plus I mean v grad v is equal to minus grad p, and plus mu grad square v, and plus rho g. So, this is how you can write the in the vector form. So, this is basically the vectors. So, here I mean it is basically written as in terms of different x, y, z coordinates. So, where here rho is basically the fluid density, p is the pressure, mu is the apparent viscosity, and grad square is the Laplacian operator, and g is the gravitational acceleration. So, so this is basically a flow chart of a typical I mean low superheat gravity die filling study. So, you can see, so the I mean so first basically we are, after putting the input data with the time increment, the iteration loop starts. So, first we are solving the momentum equation, I mean, and then we are solving the continuity. So, from momentum equation we are getting the velocity, and then we are solving continuity equation, then we are solving the energy equation to get the temperature distribution. And so, this is the energy equation, conservation of energy is written over here. So, where T is the temperature and C is the specific heat. So, please correct it. So, C is typed twice, and K again please correct it. So, K is the thermal conductivity of the solidifying melt. And here, so here is the exact text and equation from this image given. So, the fluid volume equation here. So, so in this case the fluid volume is also tracked based on the VOF technique. So, that is the resultant fluid volume equation. So, because here the VOF technique is basically used to track the free surface between the solidifying liquid melt and the I mean that and the air exposure that is at the top. So, so after solving the fluid volume equation, then these properties like the fluid properties that is viscosity, density are updated, then it is tested for convergence, and once it is filled, then I mean it is stops there. If it is not filled, then the same iterative loop starts again. So, this is how we simulate the die filling processes, and thereby we can basically optimize the getting arrangement, and also the process conditions such as die preheat, melt pouring temperature, melt viscosity, all those things. So, we basically can perform the twofold objectives we can satisfy. Number one is to optimize the gating geometry, that means what should be the so this is basically you can say this is the sprue. So, what should be the sprue dimension, what should be the in-gate dimensions. So, this is basically the tensile specimens which are shown over here. So, this is the tensile specimen, and this is as per the B557 standard, ASTM B557 standard, where we can directly get the tensile samples cast So, I mean, so according to that standard, this die has been designed, and also, I mean, this I mean, these details like in-gate dimensions, like runner dimensions, so all those things are optimized based on the, I mean, die filling study. Those results are shown to you now here. So, this is a typical solid fraction profile in case of 650 degree centigrade pouring temperature. So, this is done in case of a novel composite that we have developed within the scope of our group, that is called aluminum 15 Mg2Si and 4.5 extra silicon. So, I mean, if you are interested, you are very much welcome to refer our papers. So, this is a novel composite we developed, for which the liquidus temperature is 633 degrees centigrade. So, you can see over here. So, basically the degree of preheat here is only 17 degrees centigrade. So, I mean, why it is kept minimum preheat, that means low superheat casting is done basically to achieve minimum defect concentration. So, that is also is shown over here. So, this is a typical example of surface defect concentration profile at that pouring temperature. So, you can see where the minimum surface defects, although the higher amount of defect whichever there, that is at the top, that this is the riser section. So, this is a case of open riser. So, you can also understand the example of open riser where the riser top is exposed to the environment and it is also kept at the same height with the sprue. So, this is sprue, this is riser. Okay. So, I mean, so this is, you can understand the, I mean, a typical case study of low superheat casting, I mean, in case of using this novel composite melt. And so, now we will move into the rheological aspects. So, as you understood from the discussion so far, that in case of die filling of the solidifying melt, the viscous evolution is of extreme importance, because viscosity, why it is so critical? Because viscosity of the solidifying melt is continuously increases. Why? Because viscosity is basically function of temperature. I mean, temperature also govern the solid content within the solidifying melt Fs. So, temperature, and then it is a function of shear rate, and it is also function of the microstructure, history effect, and so on. But primarily it is can be defined, viscosity can be defined as a function of temperature or solid fraction and shear rate. So, that is why it is very important to investigate the I mean, viscous evolution, I mean, rheological behavior of the solidifying liquid melt, because that is decides whether the die design or the process parameters adopted for casting will be successful to achieve a sound structural integrity part or not, or there will be defects, or there will be I mean, not the required, I mean, the microstructure will not generate out of the upon solidification. All those things can be primarily decided by the viscous evolution of the solidifying melt. So, here rheometry is the method used to analyze the rheological behavior of a material, with rheology defined as the study of matter when it flows or it is deformed. So, as a result, rheology describes forces and deformations over time. So, viscosity we all know, however, we can discuss again. So, viscosity can where, I mean, flow can be either shear, where fluid components shear past one another. So, if you just assume there is a fluid element. So, at the top there is another, at the top there is another, and there is a relative velocity between these fluid elements. So, when so basically it is just the resistance offered by the, I mean, fluid towards its motion. So, I mean, so where fluid components either flow towards or away from each other. So, most flow occurs by a shear mechanism, and this can be easily measured using a rotational rheometer. So, how we can measure the rheological attributes of the solidifying melt? That is by using a rotational rheometer. So, rheometer can be of different types. So, I mean, based on is the rotational, based on the, I mean, measuring geometries, we can differentiate rheometers as Serle type and Cotte type. So, what are the primary differences? So, assume that this is your this is your measuring geometry. So, I mean, so this is basically, you can name it as the rotating bob, and this is the stationary cup. So, the case in which this cup is stationary and this blob, which is of course has to be a grouped one, so that it can basically facilitate shear within the liquid melt, which may be kept at isothermally at a particular solid fraction in the in the semi solid regime or in the completely superheated molten liquid state. So, this is the case of Sarle type rheometer, and then there can be a case of Cotte type rheometer as well. So, in that case the same geometry is used, however, the cup is rotating, okay, and the bob the inner geometry, which is generally grouped basic to facilitate shear. So, that is fixed. So, this is based on these differences, but the purpose is same. We differentiate rheometers or viscometers as Sarle or Cotte type rheometer. So, shear flow can be described as several layers of fluid sliding over each other, with each upper layer moving faster than the layer below it. So, that is the relative velocity concept, that is what I was telling you at the beginning. So, so the bottom layer of the fluid is considered to be stationary and the top layer has the highest velocity. So, the shear flow occurs due to the application of a shear force on the liquid, and the external shear force is described mathematically as the shear stress sigma, which is the force applied over a unit area. As the top layer responds the most to this force and the bottom layer does not respond at all, a displacement gradient is formed through the sample, which is called the shear strain. So, shear strain is nothing but your this dH. So, it is nothing but your velocity gradient, that is du dy. Okay. So, as we all know that viscosity mu can be, so it can be defined as tau is equal to mu du dy. So, this is the shear strain rate du dy or velocity gradient. That means, from here we can estimate the value of dynamic viscosity, which is nothing but tau by du dy. What is tau? Tau is the shear stress, here it is defined as sigma. So, you can see the and shear strain that is shear rate that is defined as gamma dot so then this is the resultant expression, that is here I have written it as mu, here it is termed as eta, but it is the same thing. So, it is the dynamic viscosity, that is the unit is Pascal second. We can also estimate kinematic viscosity from here. So, if you define kinematic viscosity at nu, then we can just divide the dynamic viscosity with the density to arrive at the kinematic viscosity value. Okay. So, so this is basically the mechanism what is shown here. So, shear rate, as you can understand from here, that is du dy, that means the so the unit is nothing but second inverse. So, that is what is shown over here, and so this is basically the case of a two parallel plates with a fluid in between. So, this is a typical velocity gradient which is shown. So, here because of the no slip boundary condition, velocity at the wall V w is equal to 0, and then it is at the top. So, here the velocity is maximum because it is a moving, and then this is the gradient that you can observe over here. So, that velocity gradient. So, that will be that is from here we can basically estimate the value of the dynamic viscosity. So, with this we are stopping for this class. We will start with the next class to discuss about some other case studies where we will discuss about the high pressure die casting, the die filling aspects during high pressure die casting and also during semi solid die casting. So, so till then goodbye. Thank you.